Okay, this is going to be a longer video because there's quite a few parts to it. So let's just try it. Write down the y-intercept of f. Well, that's an easy one because you just put 0 in there and it's minus 10. Show that 2 is a root of this equation. That means that 2 will make it equal 0. Well, you just put 2 in there and show that it's true. 2 cubed plus 4 times 4. So it's 8 plus 16 minus 14 minus 10. Hey, if you work it out carefully, it just does equal 0. You're subtracting 24, and 8 and 16 is 24, so that makes it 0. I've shown that it's true. Now, the big thing, if 2 is a root, that means you've got one of the factors in a bracket. So we're going to factor this. You know that x minus 2 has to be a factor. And you know because it's a cubic equation, you know it's got to be x squared. And you know you got to get minus 10, so you have to put 5 there. See, minus 2 times 5. Now you can pick any one of the things. Say 4x squared. Well, you've got minus 2 times x squared. You're going to have that. We're going to have to put something here. How do I know that it has to be 6x? Because I've got to get 4x squared. And minus 2x squared plus 6x squared, that'll make it work. That forces you to put 6x there. Now you can do the same thing looking at minus 7x, and you know, because you have minus 10x, it's got to be plus of 6x to make this because, you've got minus 12x, it's got to be plus 6x to make this minus 7x, you see? Anyways, you're worked into this now, and you can factor that last part into x plus 5 times x plus 1, x squared plus 6x plus 5. There it is, all factored. And what do we have? We know this is a cubic equation, a happy one that's taking off and going up. We call it happy and then sad, but it ends up going up at the end, and those are the x-intercepts. Now, they give you the turning points. They're kind of nasty turning points because they're all fractions. Well, it should be pretty easy to sketch this because we know the shape. The shape is that it's going up. It's concave down and then concave up. That's the shape of a positive cubic equation. Well, let's just see. Well, graphing it should be pretty straightforward. We put in the x-intercepts that we had because it was x plus 1, x plus 5 times x minus 2. So 2 minus 1 and minus 5 are the intercepts. It's concave up. So there it is. There's your first local maximum, and there's your local minimum. And we know that it's got to go through minus 10. There's everything all sketched nicely. All done. That question's done. Now let's look at the next question. Use your graph to determine which values f prime of x, where is the derivative less than or equal to 0? Where's the derivative less than or equal to 0? That means where is the gradient negative? Well, here it's positive. You see, all the gradients are positive here. Here the gradients are negative. It's decreasing here. Where is it decreasing? Well, that's in between 0.7 and negative 0.3. So that's your answer. X is less than 0.7, but greater than negative 3.4. Let's look at the next question. The next question is, the gradient of the tangent of f will be a minimum. What x value will give the gradient of the tangents to be a minimum? Now, we have lots of different ways of doing this. I think the easiest way to do it is we've got the derivative of 3x squared plus 8x minus 6. We can find the derivative. There's the equation, x cubed plus 4x squared minus 7. Just take the derivative and, where's the minimum? Well, that's just a parabola. We can get the minimum by getting the axis of symmetry, minus b over 2a. So minus 8 over 2/3, it's equal to negative 1.33. Now you can take the second derivative and go for the point of inflection. You can even look at halfway between the turning points to get the point of inflection. There's different ways of doing it, but there's that. Now, just one more question. Let's go back and look at 8.5.3. Let's take a look at that. Where is f prime of x times f double prime of x going to be less than 0? Well, that's going to happen when the two things are a different sign, less than or equal to 0, when they're different signs. So what is that going to be about? Well, if this is increasing, this must be concave down. That's when it's negative. And if this is decreasing, this must be concave up. Let's go take a look at what that looks like on the graph. Let's just go through it here. Whoop, here we are. I'm looking at the graph. This is going to help me. So where is it increasing? So I want the derivative to multiply by the second derivative to be less than or equal to 0. Well, gee, let's take a look at this. It's going to work when x is less than negative 3.4. Why? Because, well, the gradients here, the derivatives will be positive, but it's concave down. So the second derivatives will be negative, and it'll work right at negative 3.4. So there's your first answer. X is less than or equal to negative 3.4. But where's the place where they're going to be different signs? Well, here, the gradient is negative, but it's concave up. In between 0.7 and this x-intercept of negative 1.33. So x is less than or equal to 0.7, but greater than or equal to negative 1.33. Well, that's how you do it. Now, those are not so easy for most people, but whenever they have the product here, you know that the only way it can work is if one's positive and the other's negative. So you just have to think, what makes gradients positive or negative? What makes second derivatives positive or negative? There's nice explanations from this website that came through. You can read them a little bit later when you look through the slide presentation, but I think that kind of explains it.